Till now, what we have done? Do you all remember? Till now, what we have done? Rectilinear flow of heat. Rectilinear flow of heat through a bar. So in that, we ended out with what? A differential equation which was called your Fourier differential equation. And we consider some different cases. First, we consider when there was no radiation. And second, we considered steady state. And in this steady state, one of the limit which we considered is your bar is
Infinitely long.
Exactly, infinitely long. And today we are going to do which?
Finite length.
Yes, exactly. Bar of length L. Clear?
Yes, sir.
So how we are going to proceed? Finally, the solution which we ended up with was the temperature was given by A e to the power mu x plus B e to the power negative mu x. So the boundary condition for a finite length is what? First, let's consider the infinite length. What was the boundary condition for the infinite length? For the infinite length, we have considered theta to be theta naught constant at x equal to 0.
0.
Temperature to be 0 at x equal to or x tends to infinity. Clear? This was the two limit for the infinite length. So similarly, the boundary conditions for the finite length is what? Theta should be theta 0 at x equals to 0 at the left side of the bar. Left side of the bar was heated and the heat was allowed to flow in a linear manner. This is the one on your left of the boundary where x equals to 0. Now at x equal to L, our boundary condition is what? Theta should be, we don't know actually. Because it's of a finite length, so we cannot take the temperature to be 0 over here because the heat can't reach over here. So what we can do is d theta by dx equal to 0 at x equal to L. Because after here, as soon as it reaches the end of the bar, it doesn't have any more reason to transfer this heat. So that's why we can take this limit. Is this point clear?
Yes, sir.
Okay. Now again, we will again proceed in this manner. So first, let's use this boundary condition. We put it over here. So theta should be what? Theta naught or theta 0. A e to the power 0. B e to the power 0. Now we end up with exactly the same boundary condition, which was theta naught equal to A plus B. Now this is here one boundary condition. This is one of the equation. Now your second equation is you want the derivative of x to vanish. Now let's take a derivative of this. So derivative of this will be what? A e to the power mu x will be basically what? A mu e to the power mu x. And derivative of the second will be what? Negative b mu e to the power negative mu x. Is this point clear? I've just taken the derivative of this.
Yes, sir.
We can take mu common. Then it will be a e to the power mu x minus b e to the power negative mu x should be what? 0. Mu is not 0, so which means here a e to the power mu x minus b e to the power negative mu x should be what? Should be 0. Now this is your second condition. How many variables are there? 2 variables. And how many conditions are there? 2 conditions. Now can we solve for this 2 unknown variable? First, what we can do, we can substitute the value of this over here. Or easiest way is we can just multiply both sides by what? E to the power mu x. So it will be what? Theta naught e to the power mu x equal to a e to the power mu x plus b e to the power mu x. This was from your first condition. First equation times of e to the power mu x. Multiplying both sides. Now we use the second equation, which was what? 0 on this side, a e to the power mu x minus b e to the power negative mu x. Now can we subtract this two? Now after subtracting this two, what we'll get? What we'll get? This two will go out, this two will cancel out, and we'll end up with what? Theta naught e to the power mu x should be equal to how much? B e to the power mu x plus b e to the power negative mu x. Or b e to the power mu x plus e to the power negative mu x should be how much? Theta naught e to the power mu x. Clear? Or b will be how much? Theta naught e to the power mu x divided by
e to the power mu x plus e to the power minus mu x.
Is this point clear?
Yes, sir.
So can we get rid of this? Can we write in this manner, this thing?
B is equal to
Theta naught divided by, if we divide the both side by this one, or if we take out e to the power mu x common over here, then we'll end up with what? Is this point clear? We have taken this and divided on both sides. I think it's clear. This two will cancel out to give you what? 1. And over here, it will go over here to give you what? Minus 2. So this we can write in this manner. B equal to theta naught 1 plus e to the power.
e to the power minus 2 mu x.
Good. So this is your first condition. So similarly, what will be A? What will be A? Similarly, A will be theta naught divided by 1 plus e to the power twice of mu x.
Power 2 mu.
I think it's clear. We can do it explicitly also, it's not a problem. You can use in any one of the equation.
Yes.
Let's check. A plus B equal to how much? Theta naught. Now put the value of B over here. Then you'll end up with what? A equal to theta naught minus theta naught 1 plus e to the power negative mu x. Now the difference of this will give you what? Theta naught, we can take it out common. 1 minus theta naught divided by this term, which is sitting over here. And this will give you how much? Sorry, this theta won't be here. No, we have taken the theta out. So it will be basically 1 plus e to the power negative 2 mu x. So it will be how much? 1 plus e to the power negative twice of mu x. Clear? Minus 1 divided by e to the power negative twice of mu x. Sorry, 1 plus this much times of theta naught. So 1 will cancel out. So you'll end up with what? Theta naught e to the power negative twice of mu x divided by 1 plus e to the power negative twice of mu x. And this will give you what? Again, we can divide the both sides with that number. Here, sorry, we can take it on bottom and it will be e to the power negative twice of mu x plus e to the power negative twice of mu x by e to the power negative twice of mu x, which will give you what? Theta naught. This will go up and it will be positive, and this two will cancel out. So finally you will end up with what? Exactly this equation. So these are your two constant. Now what is your final step? For your final step, you have to just put this value. You have to just put this value on your main general equation, which was what? Theta is equals to a e to the power mu x plus b e to the power negative mu x. So if you put this to value over here, then you will end up with what? Theta naught by 1 plus e to the power negative twice mu x times of e to the power mu x plus theta naught by 1 plus e to the power twice of mu x e to the power negative mu x.
Sir,
This was
B
positive.
for negative.
This
Sir, B
was
ma po
negative.
minus 2x, है ना?
Okay. I'm extremely sorry. This will be positive. This will be negative. Now,
Yes,
is it
sir.
okay?
Yes, sir.
Now theta naught, we can take it out common. Now this is your final expression. Is it fine?
Yes, sir.
So this is how your temperature radiates or moves or flows in what? In your bar of finite length. Clear? But this was considered in what? This was considered in what? Steady state. Steady state.
Yes.
When your derivative of temperature with respect to time was what? 0. This was a steady state. So that's why we don't have to care about how the temperature changes with time. We just need to find how the temperature changes with position.
Yes, sir.
To summarize, here you had a bar, and this side of the region you started heating it. So it reached a certain temperature, constant temperature, which was theta naught. And at given any position, let's say over here, this was x equals to 0. This was x equal to how much? 1, 2, 3, 4, 5. How much should we take?
2.
2. Okay, 2. Then what will be the temperature over here? Let's consider one problem. So let's say, what was the temperature over here? What should we take? The temperature over here. 1 degree, 100 degrees Celsius, 2 degrees Celsius. How much?
10.
10. How much?
Yes, sir.
Only
10
10.
degrees.
10 degrees Celsius, okay. So this side of the bar was heated to reach a constant temperature of 10 degrees Celsius. So my question is, what will be the temperature at this position at x equal to 2? It's just like you're cooking. You have a fried pan, which is also made out of what? Let's say this is also made out of metal. Clear?
Yes, sir.
Do you know what is diure?
Dure, yes, sir.
Which is used for making tea
Chai
and all,
banao.
no? Oh, yes, exactly. The handle is usually made out of what? Of metal itself.
Yes, sir.
So just think of this side of the region is getting heated and it reaches a constant temperature. Let's say 30 or 50, usually it will be at high temperature, and you will be holding this over here like this something. So initially the temperature was this. So what will be the temperature of this? So whether you can hold this thing or not. Okay, that is the question. So this can be used in that manner. So let's consider that realistic case. Clear? Now you are making some tea. Do you all know how to make tea?
Yes, sir.
Okay, very good. This is how you usually make a tea. Let's say this side of the region started heating. Clear? And you have some water and tea leaves and something and milk and sugar. And you started heating this. And the temperature of this thing reached how much? 60 degrees Celsius.
Yes, sir.
Okay, 60 degrees Celsius. Now let's consider that it has attained what? It attains a steady state.
Mm,
Clear?
yes, sir.
Now the length of this handle is, what will be the length of the handle? Typical length. Half meter,
10
10 centimeter. 10
centimeter.
10 centimeter will be extremely short. Let's consider 50 centimeter. Okay, it's roughly of this length. 40 or 50 centimeter. Clear?
Yes. Yes, sir.
And you want to hold the metal bar over here. Let's consider. This is at what length? 30 meter?
30.
Okay, let's consider 30 centimeter. Because your forefinger will end up over here. So let's consider that point. So we want to know what is the temperature over there so that we can hold this or not. Clear?
Yes, sir.
So your theta will be theta naught e to the power mu x plus 1 plus e to the power twice of mu of L plus e to the power negative mu x divided by 1 plus e to the power negative twice mu of L. Clear? Is it clear till here?
Yes, sir.
So let's consider mu also to be what? We have to choose a certain value of mu. For immersive power, let's just consider it to be 1 by x. Whatever this is. 1 by x naught. Or half of x naught.
Yes, sir.
Or let's find the radiative power of 1 by x naught also. It will be 2 less. So 2 more. It will be more. So actually mu is what? Square root of E P by Ka. P was the perimeter. K was your what? What was K? What was your K? If you all remember. Sorry, K. I think I used K. Yeah, K. Conductivity. So let's
Yes,
consider
sir.
this as some value. 0.2. 0.01. Let's consider this. 0.01. Clear? 0.01 per meter. Half. Sorry, per meter, sorry. So finally you will end up with what? What was here theta naught? Was 60 degrees Celsius. What was their total length? What was your total length? 50 centimeter. 0.5 meter. So x you want to find at 30 centimeter, which is around 0.3 meter. And mu was something around 0.01 per meter. Clear? Now you have to just put it over here. Then what is the value of what is the value of this e to the power 0.01 times of 0.3 divided by what? 1 plus e to the power twice of 0.01 into 0.3 plus e to the power negative of 0.01 times of 0.3 divided by 1 plus e to the power negative twice of 0.01 into 0.3. If you compute this, how much you'll get? Use a calculator.
E to the power 0.01 into 0.3. So
Yeah.
what do you 1.003 or
Just do. Are you all doing? Are you all
so
doing?
मेरो त 1.00300 yeah.
You got something like that.
Yes.
After that, final answer. You just compute the whole thing and you just get. So finally, you'll end up with what? Everyone got the answer? With 60 itself. Have you all done? So you'll end up with what? 60. So the difference in temperature will be what? Theta minus theta naught will be 0 at this radiative rate, 0.01. Now, suppose if your radiative rate was higher. Clear? Clear? So if it was more, then what we will get? This is the difference in temperature. If it was around 1, then we'll end up with what? 54.27. So finally, we'll end up with what? 54.27. Clear? So the temperature over there will be what? 54.27 degrees Celsius. Clear? taking mu equal to 1. Is this fine? Everyone, you just check. So the temperature over there will be 54.29. So one needs to be a bit careful. Clear? Is this point clear? Now I'm just going to plot the whole thing. You just check. Now actually I've just written the same equation over here. If you can all see. I think you are all being able to see. So here what I've done is I've written exactly the same equation where T is your temperature, T naught is your initial temperature, A is your mu, X is your position, L is your length. For timing, I've taken length to be 0.5. And here A was taken to be what? 1. So that's why we ended up with this. So now let's plot how it changes over position. Now if you plot with respect to position, how it will look starting from 0 to 0.5, that was your fixed maximum length. So this is how the temperature will go away or it decreases over time. So this part is your contact. Now you can exactly see over here how this plot looks. Now you can see this is the area of contact. Now this is your handle of your, this is the handle. Basically this is a handle of that material or the thing which you are using to make tea. So this is the contact point. The temperature over there was what? 60 degrees Celsius. So as we move away, it keeps on decreasing. And finally, at the end, it will be around what? 53 degrees Celsius. At this region, it will be 53 degrees Celsius. And if you touch over here, it will be around what? If you touch around over here, this was exactly over here. It was what? Temperature was around 54. Clear? And the end of the bar will be at temperature what? 53, roughly 53 degrees Celsius. So this is how your temperature changes. This is how you find that the temperature in the rectilinear flow changes over position. So as we can see that the temperature theta over position, how it changed in a kind of exponential manner. It changes in this manner. Initially a temperature was maximum over here, which was 60 degrees Celsius, and it keeps on decreasing. This was 0.3 and it came out to be 54. It came out to be 54.3. And the end of the bar was what? It was at 54 degrees Celsius. So this is how your temperature varies over position. Is it clear, everyone?
Yes, sir.
So can you find for other different kind of medium itself, which you can relate?
Yes, sir.
Dadu. Do you know what is dadu?
Yes, sir.
Okay, what is that?
Dadu, sir. Dalu gaune dadu.
Yeah, very good. Exactly. So what is the shape of that?
Kupro ani lamu.
Okay. It's something like this.
Yes, sir.
Now
Yes.
that's a top view. But sometimes you leave it on the material or the container where you are cooking. Sometimes you leave it over here. Do you all remember? Accidentally, sometimes you leave it with over here with the container
Then
itself.
it gets.
Then it
Yes,
gets
sir.
heated. So this is a contact point. Clear?
Yes, sir.
That is a contact point. And from there, what? It will start, the heat will start moving over here. What will
Yes,
the
sir.
temperature over here that you can now evaluate? No, I think it's clear.
Yes, sir.
Okay. So that's why what do you use? You use to hold this. You call it Zumro, or it's also called MIT. In English, it's called MITs. Clear? I think it's clear till here. So in the
Yes,
next,
sir.
now what we have to do in our next class, what we have to do is we have to consider radial flow of heat. What is radial flow of heat? Can you see this is a circle? Now, if
Yes,
you
sir.
start heating at the center, then the heat will flow radially outward.
Mm.
It will flow what? Radially outward.
Outward.
This kind of flow is called radially outward. Just like an electron also here, the fields used to go outward, radially outward, it used to go. So in this here also what? The heat will flow radially outward. That you know actually. That is how it should flow. Now this kind of flow is called, this is
Radial.
for what? This is also radial flow of heat. This is basically what here? Radial flow of heat. First we have done rectilinear, now we have to do radial flow of heat. And there are two cases. What are the two cases in which we can have? Actually, there are many, but usually the kind of problem which we deal with there has two. One is
Sir,
here, spare, yes,
सर त्यो रेडियल उयो टर्बिन हुन्छ नि सर फ्लो अफ टर्बिन
yeah,
त्यो मोटरको छेउमा लाग्ने
huh?
टर्बिन टर्बिन छ रेडियल फ्लो अफ टर्बिन त्यो
Radial flow of
मोटरको टर्बिन छ
motor.
मोटरको छेउमा लाग्छ नि
Motor.
त्यस्तै खालको हो
त्यस्तै खालको, yeah. First is here, sphere, and second is what here? Cylinder. These are the two cases in what you can have radial flow of heat. Basically, radial means what? From the radius. If you draw a circle, what will be the radius? You will draw the radius like this. Avinash? Avinash?
सर
If you have a circle, then how do you draw a radius? From in this manner, you draw the radius. In this manner, you will draw a radius. Now, if you extend this is called a radially outward. Clear? So that's why it's called a radially outward. Was this point clear, Avinash?
यस सर
So similarly for the cylinder also, this is the radius. So radially outward will be what? Over here. Clear? Because we'll consider what? Small element which is circular and it will flow radially outward. And for the sphere, and second one is here, cylinder. Now there are the two cases which we have to do the radial flow of heat. So this will continue in our next lecture. And